Hello, everybody. So we are continuing to talk about our integrals. So in the last video, we talked about the fundamental theorem of calculus, and what the second part that we did told us was how to find definite integrals using what we call an antiderivative. Right? That was part two. That the integral from a to b of little f of x dx is equal to capital F of b minus capital F of a, where capital F is an antiderivative of f, right? So we need to talk about these antiderivatives because this is going to be a much simpler process to computing these definite integrals, these areas, if we can develop a good set of rules to find antiderivatives. So that's our goal right now. Let's start developing some rules. And we're going to start with some notation, and the notation is going to be for what we call the title of this video, the indefinite integral. So one thing that's clear from the fundamental theorem of calculus is there's this connection between integrals and derivatives, and in some sense they undo each other. They're sort of like inverses with a little bit of they're not quite there, but they're pretty close to being inverses of each other, right? They undo each other. So with that in mind, we're going to steal the symbol from the definite integral and use it in relation to the derivative in the antiderivative, right? So it's because it's undoing it, we're going to use it as an antiderivative symbol. So what I mean by that is that we will write, so here's my integral symbol, but notice there's no bounds on it. So if I write the integral of f of x dx is equal to capital F of x, this means that capital F of x's derivative is equal to f of x, little f of x. In other words, this is saying that capital F of x is the antiderivative of f of x. Okay, so that's just notation, right? It's just so that we can have a nice symbol for antiderivatives. The integral one makes sense because it's so related to antiderivatives. So it's a good kind of locks in that connection in our heads. So we want to talk about antiderivatives. We have to be a little bit careful. So I briefly mentioned something in the last video that I want to expand on a little bit before we get into actually finding antiderivatives. If I have two functions, f and g, with derivatives that are the same, it turns out that these two functions are the same except for a constant, right? This constant can be any real number. So that's, this set of symbols just means C is in the set of real numbers, okay? So why is this true? Let's take a look at this quickly. If I have two functions whose derivatives are equal, I'm going to invent a function called h, which is f minus g. Then h prime is equal to, just using the rules of derivatives, h prime is equal to f prime minus g prime, right? And since these two are equal, that's equal to 0, right? H prime is equal to 0. Okay, so I'm cheating a little bit, right? Maybe you haven't seen this before. So when I'm writing f prime equals g prime without that of x or of t, I'm just saying over its whole domain. Okay, so I'm obscuring the input a little bit here, because I'm just proving something about the functions in general. Well, if h prime equals 0, this is something that's learned in differential calculus in a previous course. If h prime is equal to 0, then h has to be a constant function, right? So using that symbol again. But that means h is equal to f minus g must be equal to a constant function, which is really just saying the difference between f and g is a constant, right? Or we could take this piece of this equation, add g to both sides, and get the claim from the beginning. F is equal to g plus a constant, okay? So there's our little quick sketch, quick proof of this fact, okay? Why is this important for us? Well, when we find antiderivatives, we are actually finding a family of functions, because if given a function and its antiderivative, any function that's the same as that antiderivative you found plus or minus some number is also going to be an antiderivative. Let's do an example of that, and then we'll really, I promise, get into developing our rules. So let's do this. Well, we'll see what, there's a picture down here that we're going to look at in a moment. We'll see what this thing does for us shortly. Let's just move it out of the way for now. Let's look at, the following functions. F of x, I'm going to let f of x be equal to 4x cubed plus 6x squared minus 2x minus 2. And I'm going to use this symbol. Sometimes we say the antiderivative of f of x dx, or the antiderivative of f of x is. So I'm just going to write one. Right? I'm just going to write this. Don't worry about where I'm finding this. You might recognize how I'm doing this. Okay. So what I'm saying here is, remember, this means, let's say it this way, the derivative of the right-hand side, x to the fourth plus 2x cubed minus x squared minus 2x is equal to f of x. And indeed, if you take the derivative on the left-hand side, you get 4x cubed plus 6x squared minus 2x minus 2, which is equal to f of x as defined above. Okay, so without knowing where I got it from, I found an antiderivative. Notice, however, that I could also take the following function. Let's do a negative one. I keep putting positive. Minus 3.952. Right? Well, if I take this this derivative, I get 4x cubed plus 6x squared minus 2x minus 2. The constant disappears. We have the same derivative. So both of these functions, this first one I wrote down here, and this one I wrote down here, are antiderivatives of lowercase f, right? So in other words, I could say something like this. I could let capital F of x be equal to x to the fourth plus 2x cubed minus x squared minus 2x. This is an antiderivative of f. But as we saw, this constant where I subtracted this constant is also an antiderivative. I mean, it wouldn't matter which constant I added or subtracted here. So sometimes what we'll do, and often what we'll do, is we might write instead that the antiderivative of f of x is going to be x to the fourth plus 2x cubed minus x squared minus 2x plus, and we just write c to represent plus any constant, okay? This is no longer a function, it represents a family of functions. Right. And that's what this picture, oops, I don't want to do that, what this picture is. This is the family of functions, or at least some of the family of functions that we are looking at here, right? The one we computed, this original f of x, is the one that goes through the origin at 0. If I, for instance, add 1 to it, I get this function. It has the same shape. I've just shifted it up, right? At each point, we've moved up 1 unit. Right? Each point, we've just moved up 1 unit. Here's one where I've subtracted 3, right? And this goes on and on and on. So this picture that we're looking at here is a family of functions that are all antiderivatives of lowercase f, okay? And so we will want to keep track of that. And so the habit we want to get into is, here's kind of our base antiderivative of lowercase f. We always want to write these plus c's, okay? This is going to seem like an annoyance often, but it turns out these plus c's are going to have some meaning, and we'll see that shortly. I'm not going to worry about it in this video, but it does tell us some extra information depending on what these functions represent, okay? And so we need to get into the habit of remembering them. And so I will insist that we have these plus c's at the end of our antiderivatives. Okay. Let's move on. So now we're really going to get into developing some rules, we'll say rules of anti-differentiation, okay? And the way we're going to develop them is really just by thinking things through, right? It's almost like a guess and check game. Which might seem a little silly, but this is a game you've played before, right? When you go find a square root, if you don't have a calculator, how do you find the square root of 36? You don't find it, you remember that 6 times 6 is 36, right? And if I asked you to find the square root of 37, you would say, well, I know 6 is close, it's gonna be a little bigger, and you can start to finagle it a little bit, do some guessing and checking. We're gonna do a little bit of that here to develop a set of rules for our basic antiderivatives. What this really is, if you remember back to learning derivatives, right after you learn the limit definition of a derivative, the next thing people usually do is start learning shortcuts so they don't have to use that limit definition. And there's kind of, before you get into the complicated rules like the quotient rule and the product rule, there's kind of a set of simpler rules that are usually presented in a table. We can just read that table backwards. So for instance, let's come up with a few rules here. First, we'll have some kind of like basic properties of these antiderivatives. Suppose I want to take the antiderivative of a constant k times a function x, f of x, right? Well, suppose I knew an antiderivative. Let's do some work over here on the side. Suppose I had an antiderivative of f of x equals capital F of x. Right? Now let's take the derivative of a constant times f of x. Our derivative rule says that constant can come out front. And we get k times f prime of x. But we know that capital F of x is an antiderivative of f of x, so this means k times capital F of x is an antiderivative of k times f of x. Okay? In other words, this constant just kind of slipped through everything. Right? So in other words, we can take k times the antiderivative of f of x, right? That's what this is saying. So if you have an antiderivative of the function f, if you want the antiderivative of k times that function, you just take k times the antiderivative, which is what we did right here. Okay? So that's our first rule. With these indefinite integrals, constants that are multiplied to the whole integrand can slip through to the front. Here's another one. If I have the antiderivative of the sum or difference of two functions, I can take each of them separately. Right? I'll let you work this one out on your own, but it comes straight from the fact that that derivatives distribute over addition and subtraction. Okay. All right. Now let's work a little. Let's get into some more specific rules. Suppose I want to take k here as just a constant. Suppose I want to take the derivative, the antiderivative of a constant, right? What things do we take derivatives of and get constants? Well, things like, so again, I'm just doing some scratch work on the side. We'll keep all our rules over here on the left, and I can use this side to do a little remembering. For instance, if I take the derivative of 2x, I get 2. I get a constant. If I take the derivative of 3x, I get 3. I get a constant. In other words, the constant times x is an antiderivative of that constant, because if I take a derivative of what's on the right, I get the function k, the constant function. Okay. However, we want to write the entire family of functions, which is k times x plus some constant c. Right? Let's think about the meaning of this. What we're really saying here is the derivative of a linear function is its slope. And so we're looking at the family of all the parallel lines with the slope of k. All of them have the same derivative of k. Okay? Which means these functions are the antiderivatives of k. All right. Here's one that's a little more complicated. Suppose I have x to the n dx. So x to some power. So I'm trying to find a function whose derivative has x to a power of n. I know when I take derivatives of power functions, I take away one power from the exponent. So if I want to get to n by taking a derivative, I must have n plus 1, because when I take the derivative, this power becomes n. However, when I take this derivative, let's do some more scratch work. I'm going to get rid of some of this. When I take this derivative, if I took the derivative of x to the n plus 1, I do get x to the n, but I get a constant of n plus 1 that I don't want. However, if I put n plus 1 in the denominator, that's a constant. It goes along for the ride. I'm left with just x to the n, which tells me that this function is an antiderivative of x to the n. And then, of course, I'll add my constant. Okay? Now, there's a problem with what I just did. Let's see what the problem is. So let's do x to the negative 1 dx. According to this rule, if I have x to the n dx, I should take x to the n plus 1. So here n is negative 1. Negative 1 plus 1 is 0. And I have to divide by 0. This is very problematic. We can't divide by 0. Okay? So something's wrong with negative 1. Well, can we think of a function? This is x to the negative 1, or 1 over x, whose derivative is 1 over x. We probably remember natural log of x. Okay? So this rule doesn't work when n equals negative 1. It will work for all other numbers, and we need a special rule for when x is the power is negative 1. We get the natural log, and it turns out we have to do absolute value of x, because this is also true, and this is the most general form of that antiderivative, right? We're trying to find the most general form, right? We don't want one specific, we want the kind of largest family of functions. Okay, so what do we have? What do we have next? Here's a maybe easy one. We're looking for a function whose derivative is e to the x. Well, we know e to the x has a derivative of e to the x. And then we have to add our constant. We sometimes call these constants of integration, right? Because they come from our integrals. This one's a bit less easy. What about instead of e to the x, we have some number to the x power, right? Here, a would have to be non-negative. Well, we might have to do a little work to remember this one. If you take the derivative of a to the x, you get a to the x back, but you also pick up a constant natural log of a. Okay, but we don't want that constant there, so we can kind of use the same idea we used up at the top here. We wish this constant wasn't here. We could divide by it, and if we divide by that constant on this side, it doesn't change the derivative other than having the constant in the denominator, which cancels it out, which means a to the x over the natural log of a will give us the antiderivative. Okay. All right, keep moving. Let's see. How about the antiderivative of sine of x? Dx. We just need to remember that if we take the derivative of cosine of x, we get sine, except we get negative sine. So if we start with negative cosine, we'll get positive sine of x. Remember what we're doing in each case. The thing I write on the right, if you take its derivative, you get the thing on the left. Okay, that's the meaning here. We get cosine of x, antiderivative is just going to be sine of x. We'll get secant squared x dx. And all of these I am just getting from memory. And I'm just remembering that the tangent of x has a derivative of secant squared. Cosecant squared of x, I have to remember that the cotangent has a derivative of negative cosecant, so I'm going to have to put a negative in front of it to make it positive after I take the derivative. And then we can also do secant x tangent x dx. This is the derivative of secant. So secant is an antiderivative. Keep moving. We've got, what else? Cosecant x times cotangent x dx is going to be negative cosecant x plus c. So we've got a couple more to do. I just want to make this perfectly clear, a couple of things. First of all, to see that we're correct, we can just take a derivative of what's on the right and see that we get what's on the left. I know especially the last four might not be as familiar. You can jump back to whatever textbook you used for differential calculus. There's probably a table in it that you can remind yourself. They probably derive where these come from. A lot of them use things like the quotient rule or the product rule to come up with these derivatives once they get sine and cosine. And all we're doing is using that knowledge from before to remember these antiderivatives. If I take the derivative of the thing on the right, I get the thing on the left. We're going to do two more. These turn out to be useful to us down the road. We'll see a lot of things that come in this kind of a derivative or antiderivative, this kind of function, 1 over x squared plus 1. And we remember that this has an antiderivative of inverse tangent x, because if you take the derivative of tangent inverse of x, or inverse tangent of x, you get 1 over x squared plus 1. And one more like that, 1 over the square root 1 minus x squared dx equals sine inverse of x plus c. Okay, all right, that was a whole bunch of stuff. okay? So while this seems like a huge list, and these are definitely things you're going to want to know, I believe the first 7 or 8 for sure will become really, really, really obvious to you really quickly. The trig ones, the sine and the cosine come pretty quick. The other ones you might have to take some time memorizing. And certainly it's all right to have to look these up once in a while, right? I, for instance, forever confuse the antiderivative of secant squared and secant tangent. Every time I do this, I have to remember which one's tangent and which one's secant. These come up a lot, and for whatever reason, they won't stick in my head. So I have to, do my best to remember, and one of these days I will get it. We can also use these rules in combination. So let's do a few examples before we finish up. We're going to use a bunch of these rules. So let's see, I think I can maybe, let's do this. Create a little more space. And I think I'll get rid of the scratch stuff for now. I want to be able to refer to these rules a little bit. Because already, even though we have a list that's got, a few things on it, we get even more out of these rules when we use them in combination. So let's do a couple examples of that. For instance, let's take the antiderivative of, let's just make something fun, like 3x to the 5th minus 2x squared plus 7. Right? So I'm going to use a whole bunch of these rules. The first rule I'm going to use, maybe I'll number these a little bit. Here's 1, here's 2, here's 3. I'm going to use a couple of these soon. And this one, we'll number more as we need them. So first rule I'm going to use is number 2, which tells me I can split up this antiderivative into 3x to the 5th dx minus the antiderivative of 2x squared dx plus the antiderivative of 7 dx, right? So I'm just using this rule that I can split it up into 2 different antiderivatives. Now I'm going to use rule 1 that tells me if I have a constant times a function, I can bring the constant out front. I'll use it again here to slide that 2 out front. And I'll leave the 7 alone for now. All right, now I've got the antiderivative of x to the 5th dx. Looking at rule 4, this is a power of x where it's not the power of -1. So the antiderivative is x to the 5 plus 1 over 6 divided by 5 plus 1, or 6. Minus 2 times, and I'll use that rule again, x squared. If I have x to a power that's not -1, I add 1 to the power. So I get x cubed, and I'm going to divide by that same power. Finally, I have a constant. Rule number 3 tells me if I have the derivative of or antiderivative of a constant, I get that constant times x, and then I'm going to add my plus c. Okay? And that's it. I'm just applying all those rules. I might want to simplify a little bit. Doesn't really matter. 1/2 x to the 6th minus 2/3 x cubed plus 7x plus c. This is going to be my antiderivative, of this function. Okay. Now, a really good skill to have when you're first learning how to do something is how do you tell if you're correct? Right? In most cases, it's been my experience, taking derivatives comes more naturally than antiderivatives, right? I think this is very, very akin to a lot of inverse functions. Squaring numbers is easier to think about than taking square roots. Taking the exponential of a number is easier than taking the logarithm of a number, right? Or inverse trig seem to boggle a lot of our minds. So what we can do to check our work is use the easier process. writing this down, what I've written here, the antiderivative of 3x to the 5th minus 2x squared plus 7 is equal to 1/2 x to the 6th minus 2/3 x cubed plus 7x plus c. When I wrote that, remember what our definition of the antiderivative was. Slide up for just a second. This means that the thing I got as the antiderivative, its derivative is the thing I started with in the indefinite integral. So let's show that that's true. Let's take the function on the right and let's take its derivative. All right, so I can take each derivative individually. Using rules of derivatives. All right. Derivative of 1/2 x to the 6th. I pull the 6 down. 6 times 1/2 gives me 3, and I've got x to the 5th. Take the derivative of x cubed. I pull the 3 down, multiplied by 2/3 gives me a 2, and I lower my power by 1. I get 2x squared. The derivative of 7x is 7, and the derivative of a constant is 0. And we see indeed that what we got was the function we were taking the antiderivative of. Okay? So this is, especially in the beginning, imperative that you use the derivative to check your work. The result of the antiderivative, you take its derivative, you get the thing you started with, right? When I take the square root of 36 and get 6, I know it's right because 6 times 6 is 36. I go back in the other direction. All right, we'll do a lot more examples. I think this one's gone on long enough. We'll do a bunch of examples of combining these rules and seeing what else we can do. This is our first set of rules for solving these antiderivatives. What I've just shown you here is, besides what's listed in these rules, we can do every polynomial, right? Every polynomial will be exactly like what I just did here. Split it up into all of its individual terms, slide those constants out front, and apply the power rule. And we can do all the polynomials. Okay, we'll do another video with a bunch more examples soon. All right, I will see everybody next time. Thank you for coming.